All right, guys, we have finally finished exponents and scientific notation, except now what we're going to do is take everything we learned from those lessons and apply it to exponential growth and decay. So notice that right away in the name, we have exponential or exponents. Okay, so everything we're doing through this is going to utilize what we've learned about exponents. So we're going to start with exponential growth, and what exponential growth says is as our x, or the input, okay, remember x goes across our horizontal axis, as that increases, so we get higher and higher and higher, then our y, the output, look what our graph is doing, it's also increasing. So everything on our graph is staying positive. It's going further to the right, which is more positive, and we're going up, which is also getting positive. So here we have the form of our exponential growth equation, y equals a times b to the power of x. Notice that there's that exponent right there, which tells us how much we're changing. Okay? So a is going to be our initial amount, kind of where we're starting out, and b is our growth factor. Now our growth factor is the sum of 1, okay, so we always have a number 1, and the growth rate. So the rate at which something is changing or increasing. So if something is doubling or it's increasing by a rate of, 50%, that's going to be our R. So you might see it look like this. So the alternate form will be y equals, we keep the a, but instead of b, we have 1 plus r all to the power of x again. All right, so for these first couple of examples, we're just going to identify things. We're going to identify the initial amount, the growth factor, and the growth rate. Now we're just following the form of our equation. So we've got y equals 3 times 1 plus 0.05 to the power of t. So our initial amount is going to be 3. It's our a value. Our growth factor is the 1 plus 0.05, or we can write it together as 1.05. And the growth rate, okay, the rate is just what gets added to the 1, so this is 0.05. All right, number 3 looks a little different because we have this f of x. Remember, that's the same thing as y. So I could write this as y equals 750. And instead of 1.25, I could write that as 1 plus 0.25, all to the power of x. Now, the reason I would maybe do this is so I could say, okay, my growth factor is 1 plus 0.25, which I could leave as 1.25, but splitting it allows me to see that my growth rate is 0.25, and my initial amount was 750. Now number 4 looks also a little different because it's got this 3 out front of the y. Now I don't care about 3y, so I'm going to divide on both sides by 3. On the left they cancel, so I've got y equals, and then 900 divided by 3 is 300, times the 1, and I'm going to write this again, I'm going to split it as 1 plus 0.85 to the power of x. Okay, take a second and look over those answers at the bottom here. All we did was identify the parts of our equation. All right, now we're going to take a minute and we're actually going to apply our equation to some application problems. Our first one here is about Jill. So read this problem and then we'll work through it together. All right, so Jill is investing $1,200 at a percentage rate. Okay, notice we got the word rate there of 6.8%. We're doing two things. We're writing the function, and then we're going to find the value after 20 years. Okay, so we're going to write down our equation. We've got y equals a times 1 plus r to the power of t. Okay. Now we're going to fill in what we know. So my initial amount, what I'm starting with, I have $1,200, or Jill has $1,200. Our growth, we're doing 1 plus my rate of 6.8%. Now 6.8% we have to write as a decimal, and that looks like 0.068. And I'm going to keep the t for now. So this is our function we're going to work with. and the t is going to represent time. So now what we're going to do is part 2 of our problem is find the value of the investment after 20 years. So I'm going to keep my equation, y equals 1200 times 1 plus 0.068, but I'm going to change the t to the 20 for 20 years. All right, so I went through the problem here. I simplified my decimal to 1.068 to the power of 20, and at this point, you can just plug this into your calculator. Okay. Anytime you're using the exponent, you might need the little caret on your calculator button. So it kind of looks like an upside down V. Okay. And that will insert an exponent for you. Well, you should have gotten an answer of $4,473.08. And remember, word problems, word answers are units at least. So you should have a $sign too. So give E a try here about Heritage University. Okay, before you get too far, here's the function you should be working with. They started with 7,780 students. We're increasing by an average of 4.5%, which is 0.045, and we're going to keep the t for time. So go ahead and solve the second part. How many students would they have in 2025? So when I clean up my equation, okay, so I come over here, I've got the initial amount of students. I simplified my numbers in the parentheses, and my exponent was a 7 because it was a 7-year difference between 2018 and 2025. I got a total of 10,587 students. I had to round down because I didn't quite have enough for 10,588. So I round down and word problem, word answer. All right, switching gears from exponential growth, we're going to go to exponential decay. Now, decay, if you think about something that's decaying, it's losing value or it's something's going down. So our input is increasing, right? We're still going across to the positive numbers on X, but look at our Y, our output is coming down, it's decreasing. Okay, so not much changes except, so A is still our initial amount, okay, and B is our decay factor now. Okay, instead of growth factor, we're decaying. And the decay factor is the difference of 1 and the decay rate. So all the words are kind of the same, except instead of growing and adding, we're decaying and it's the difference. So B is 1 minus R. So here's our formula we're going to work with now. So we've got 2 practice problems here where we're going to do the same thing. We're just going to identify the initial amount, the decay factor, and the decay rate. So my initial amount is this number on the outside, it's 12. My decay factor is everything in the parentheses, so 1 minus 0.09. I can simplify this to 0.91. And my decay rate is what's being subtracted, so 0.09. Go ahead and give number 2 a try. So for number 2, the decay factor was already simplified for us in parentheses, the 0.85. But to figure out the decay rate, you kind of have to work backwards. What number is being subtracted from 1? And that would have been 0.15. So your initial amount was 24,000, decay factor is 0.85, and decay rate was 0.15. All right, we're going to work through an application here about Don, who purchased a Mustang for $39,995. The car value depreciates. That's another word for like it's decreasing in value at a rate of 13% per year. You're going to write a function and find the value of the car after 6 years. Okay, so we're going to use our exponential decay equation. So y equals a times 1 minus r to the exponent of t, where t is our time again. The initial value of the car is how much Don paid for it, so the $39,995. Our decay rate, we're going to have 1 minus our 13%. It's depreciating by that much each year. So 1 minus 0.13 to the power of t. So that's our equation we're going to use. But now we have a second part where we have to solve for the value of the car after 6 years. So using our equation, we've got y equals 39,995, 1 minus 1.3, and our exponent's going to be a 6. All right, so after you simplify your parentheses, you've got the 0.87, you've got the power of 6 here, and after 6 years, Don's car is only going to be worth $17,342.88. All right, we have 2 more real-world examples we're going to talk about, and our first one is going to be compound interest. So this one says, how much will be in an account after 30 years if $8,500 is invested at 9.25% compounded monthly? Now that's a lot of information, a lot of details, but there's actually a really nice formula to work with here. So A, our account balance, however much money we have in our account, is equal to the principal. So this is how much money you put in the bank, okay? So in this scenario, we have $8,500, and there's a little piece here missing where it's not just our rate that we have to add to 1, but it's the rate divided by n, or the number of times the interest is compounded per year. So when you set up an investment, there's different options on the number of times you will compound your interest each year. There's different interest rates, which the R is, and we are keeping our power here where we have the number of times our interest is compounded times the time in years. So if we do this for 10 years, t would be 10. If we did it for 6 years, t would be 6. So all we have to do here is plug in all the numbers we have. So our account balance is going to be equal to the $8,500 we started with times 1 plus our rate is 9.25, so that looks like 0.0925, divided by, we're compounding monthly, so that means each year we're compounding it 12 times, once per month. And this all goes to the power of, we've got the number of times per year, 12 times the number of years we're doing, which is 30. It's a lot, but it's a lot of just plug it in and put it in your calculator. So let's clean this up a little bit. All right, I cleaned up my parentheses a little bit. My fraction becomes about 0.0077 to the power of 360. And when I plug this in and simplify everything, I'm looking at a total, remember we're in money, so in dollars, I have $134,885.40. So that means we took our $8,500 investment and we made it into $134,885.40. All right, we have one more example, and that's going to be radioactive decay. Now, you might have studied this or heard about this in science class. And again, it's a lot of information, but it can all get plugged into our calculators pretty easily. So our formula is we have whatever we're working with, whatever we have left, is equal to the initial amount, okay, what we start with, and in our parentheses is the half-life. Okay, so we're gonna plug in 1/2. Okay, and our exponent, notice, is a fraction. So if we look at our example, radon has a half-life of 3.8 days. If there are 35,000 milligrams of radon, how much will remain after 4 weeks? So when I plug in all my information here, I'm left with 211.8 milligrams of radon. Now, the only thing to take note of is that my exponent has to be in the same units. So instead of weeks, I need days.